measured from the optic center to the principal focus is called the focal length of the lens. The lowercase f, the same we use for the mirror. So the focal length is the distance from the optic center to the principal focus. Now, image is formed by a convex lens. Again, in order to locate images, you can see we can take a ray that is parallel to the principal axis. After refraction, it will go through the principal focus. A ray that passes through the optic center will not deviate. It will go straight on. A ray that passes through the principal focus after refraction will go parallel to the principal axis. Any of these three rays, any two of these three rays will be enough to construct the image. In the same way as we used for the mirrors, if u is the object distance and v is the image distance, well, if u is the object distance and v is the image distance, then and f is the focal length, then we have 1 over f equal to 1 over u plus 1 over v, which is the same as in the case of the mirrors. Now, the magnification m produced by a lens is m equal to height of the image divided by height of the object, which is again v over u. Well, let's use that to solve the problem. A 4 centimeter tall light bulb is placed at a distance of 45.7 centimeter from a double convex lens having a focal length of 15.2 centimeter. Determine the image distance and the image size. Well, now picking the data we have, the size, the height of the object is 4 centimeter, object distance is 45.7 centimeter, focal length is 15.2 centimeter. We can use these two quantities to find the image distance using the lens formula. This time we call the formula the lens formula. And that will give you v equal to 22.8 centimeter. And once you have v and the value of u, we can calculate magnification. Magnification is v over u, and that will be 0.5. That means the image size is half of the object size. And of course, magnification is related to height of the image and height of the object. 0.5 is hi divided by ho. That gives you the height of the image is 2 centimeter. Now, lenses are used to correct vision in nearsighted and far-sighted people. Most of you, I'm sure, use lenses. For a nearsighted person, images of objects placed far from the eye are formed in front of the retina, and so a diverging lens is used to create an initial divergence so that the final image will be formed on the retina. On the other hand, for a far-sighted person like me, I have far-sightedness, but I don't wear glasses because I can see at a distance, not near. Now, for a far-sighted person, images of near objects are formed behind the retina, and that's the reason why when I want to read something without my glasses, I take it away. Now, to correct that, we use a converging lens so that the lens will produce an initial convergence. Alright, what's the meaning of power of a lens? Power of a lens is the reciprocal of the focal length, and focal length must be measured in meter. And then the power will be measured in a unit called diopter. So the power of a converging lens of focal length 20 centimeter is 1 over 0.2, which is 5 diopter. Now, all these things will be revisited in one of the labs that we will be doing. The power of a diverging lens of focal length negative 20 centimeter is negative 5 diopter. Now the power of a converging lens is positive, the power of a diverging lens is negative. We are now going to look at another important characteristic of light, interference of light. Now, in the discussion on wave motion, we talked about how two waves meeting at a point can either produce a bigger wave or no wave at all. Now the question is light a form of wave? Now this has been a question of debate in the past. Some scientists say light is made up of particles like photons, but some others say light is a form of wave. Now who do we believe? Well, we cannot believe anybody, we can only believe or trust evidence. So, can light undergo interference? Can a beam of light meeting with another beam of light sometimes produce no light or sometimes produce more light? Is that possible? Well, light consists of transverse oscillations of electric and magnetic fields. We talked about that in the last class. And at right angles to the direction of propagation. Now, just considering the oscillations of electric fields, these waves can be represented as E of t is E0 sine omega t. We found that in the last lesson. This is how the electric field varies with time. Another wave of the same frequency and wavelength of slightly different phase, how will you represent that? Another wave of the same amplitude, frequency, but slightly different in phase. We can write it as E prime t is E0 sine omega t plus delta, where delta is that phase difference. Now, if these two oscillations fall at the same place, how do they interact and what will be the resultant wave? If these two waves meet at a point, what will be the resultant electric field vector at that point? That will be E0 sine omega t plus E0 sine omega t plus delta. And if you use, we have actually used this in connection with discussing wave motion. So when you expand this, it will be 2E0 cos delta by 2 sine omega t plus delta. And I use this in red because this is the resultant amplitude of that vector. And the resultant amplitude will be 0 when half delta is pi by 2, which was cos pi by 2 is 0. And this resultant amplitude will be 2 epsilon naught when half delta is 0 or 2 pi. You see that? So the amplitude of the resultant wave is 2E0 cos 1/2 delta. When the phase difference delta is an integer multiple of 2 pi, what will be 1/2 delta? The amplitude of the resultant wave will be maximum, and namely 2 epsilon naught, and the resultant intensity will be a maximum. Now, so the resultant amplitude is 2 epsilon naught cos 1/2 delta, and as a result, if the phase difference delta is an integer multiple of 2 pi, then 1/2 delta will be 0, pi, 2 pi, 3 pi, and so on, giving the absolute value of this to be 1, and the resultant amplitude will be 2 epsilon naught. On the other hand, now, such an interference is called constructive interference. We have actually seen this earlier. On the other hand, if the delta is an odd integer multiple of pi, if delta is pi, then cos pi by 2 is 0, cos 3 pi by 2 is 0, cos pi by 5 pi by 2 is 0, the intensity will be 0 for all such delta values. Now, this is called a destructive interference. That means a beam of light can actually constructively or destructively interfere. Light falling on light can produce more light or no light. So what do you think light is? Now, it was Thomas Young who demonstrated this effect first, which conclusively proved that light has a wave characteristic. So does it mean that people who argue for the particle nature of light has to give up and say, well, we are wrong? Well, not so simple, but what we have now seen is light has particle nature. Now, let's look at the double slit experiment Thomas Young did. Now, what Thomas Young did is he cut two narrow slits on a screen and allowed a monochromatic light, a light of one color, to pass through the